In this video, we're going to talk about references, which is sort of like the second part of the pointer story. That would also lead us to a brief discussion about the const qualifier. Here in VS Code, I'm back to a very simple program where I once again declare and initialize two integers x and y. Now, a reference is a variable that is a direct fixed link to another variable. So let's declare and initialize references to x and y. I'm going to once again copy and paste the integer declarations and turn them into reference declarations. So let's call our references r and s. And then to declare a reference, you use an ampersand adjacent to the variable name in the declaration. And then to assign a reference, you just set it equal to whatever variable you're assigning to. So we'll set the reference r to equal to x and the variable s to equal to y. Okay, so far so good. Now let's put in some print statements so that we know what is going on. So I'll copy and paste this 4 times once again for all of the variables that are involved. Let's save this and compile and run it. Okay, so no real surprises here. We see that the values of x and y are 1 and 2, and the values of the corresponding references are also 1 and 2, because r and s are the references to x and y. Since references are direct and fixed links to variables, we can expect that changes to either the reference or the variable would affect both. So let's have a look. So I'll first change the reference r to 10. So I'll say r equals 10. And I'll copy my print statements. And I'll say here that this is after changing r. And I'll save this and run it. And we can see that both r and x got changed to 10. So by changing the value of the reference, we have affected the variable itself. Likewise, we can change the value of x, and it shouldn't be surprising that it would affect the reference as well. So here we'll say x equals 5, and this would be after changing x. I'll save this. I'll recompile and run things. So we can now see that both r and x are 5. Now, something that is special about references is that they cannot be reassigned. So after you have initialized your reference and you assigned it to some variable, the reference is going to stick being assigned to that variable. So for example, we have r being a reference to x. If I was to set r equals y here, what this is going to do is it's just going to copy the current value of y into r. And of course, that would affect x as well. So let's put a set of print statements in here again. So this would be after r equals y. We'll save this. I'll clear the console and compile and run. So now we see that everything is 2. And that is because we copied the value of y into r, which affected x as well. However, if I was to now change y, say I wanted to change y to 100, that would have no effect on x. So let's have a look. So after y equals 100, and let's run this. So what I see here is that it's only y and its reference s that got changed to 100. R and x are still 2 from the previous change. So it's only the immediate value of y that was copied into the reference here. Any subsequent changes to y don't affect the reference. Just like with pointers, the real beauty of working with references comes in once we start working with functions. What I have done here is I have cleaned up the code that we were working on thus far. What we have here is the declaration and assignment of two integers x and y. Then we have the declaration and assignment of two references to those integers r and s. Finally, I have added the declaration and assignment of two pointers to those integers p and q. And this is the exact same declaration and assignment as we had in the previous video. We have some print statements here. And then I have added the different versions of the add function that we developed in the previous video. In particular, in this version, we applied pointers to implement some form of pass-by-reference schematics such that the changes done on line 9 would be communicated back to main without using a return value. As you can imagine, references probably have something to do with pass-by-reference. And indeed, we could use references to get rid of some of this clumsy pointer notation. So what I'm going to do is that in this version of add, I'll take out the stars and I'll replace them with ampersands. And then we'll get rid of the stars here because we no longer have pointers and this doesn't quite make sense. So now x and y are being passed by reference into this function. What that means that anything that happens here is going to be communicated back to main. And in fact, just to have the regular addition, we probably don't want to have this line here because it's just going to confuse things. So let's go back to main and we'll make a call to this function. The only thing is that when we are working with references, overloading no longer works. So we should change the name of this to add1 and this one to add2. Then we can go back to main and we can make a call to add2 right here. And we'll pass in r and s. And I'm going to save this and let's compile and run things. And we do see that the value of x is now 3, and that's because add2 took in the references and it did add x and y and saved the result into x, and the changes are seen in main. Now, if we have also had this line here, then of course it would override whatever we did here and we would just be getting x equals y as a result. So if we compile and run this, we do see that x is equal to y. Both of them are 2. So let's just get rid of this, not to confuse things. And now we see the symmetry between add1, where we are passing things in by value, and it has no effect on the way things happen in main. And then we see here add2, where the only difference is that we have placed the ampersands here, and we're passing things in by reference, and this does affect things in main. And indeed, we don't even need to explicitly define references RNS for this to work. We could have just passed in X and Y here, and then the result would be the same, because essentially they get passed in by reference. And this is why you can't overload this function anymore, because you have to explicitly specify, do you want to go in by value or in by reference? And once again, this is something that we wouldn't been able to do in Java, because in Java, essentially, well, as far as integers are concerned, they're all primitive, can't really do anything. But in C++, you can just stick the ampersand on whatever you want, and it would get passed in by reference. Then, when it comes to this version of add, where in the previous video, we applied double pointers to pass the pointers themselves in by reference, so that we could reassign the destination of pointer x on this line here, and have it communicated back to main, without having a return value. Now, references could also be used to make all of this notation here less clumsy. So I'll change one of these stars to an ampersand. And what we have here now for the parameters of this function are pointers being passed in by reference. And then we can get the rest of this to make sense. So if you want this line to make sense, obviously we don't need the extra star here. And then in here, we're just going to have x equals y. And this is going to be the line that's going to change the destination of x and communicate that back to main. And then so let's name this add3. We don't really need to do this because at this point here, we're working with pointers. So we can overload this. It's not going to clash with the add1 and add2. But just for consistency, I'm going to make this into add3. And then I'll copy and paste this here. And I'll say that this is now add3. And I'm going to pass in P and Q because those are my pointers. And I'll say here that this is after add3. And I'll save this. And let's clear the console, compile, and run things. And we see that after add3, we do have the P and the Q pointing to the same address. So we know that this line here worked, and that's because the pointers were passed in by reference, and that's because we have the ampersand there in the declaration of the function. Finally, let's take a look at how references work with classes. So what I have here is the declaration and implementation of a very short, silly class. In fact, it's almost the same class that we used in the previous video. So we have name and ID for fields, we have the constructor that uses the shorthand notation, and then we have the getter and setter for ID. We also have two functions. Both of them take an instance of the sample class as a parameter, and they both want to set its ID to 2. The only tiny difference between the two functions is the ampersand. So here we are passing the sample class in by value, and here we are passing it in by reference. In main, we construct an instance of the sample class with name hello and ID of 1. Let's call the two functions on this class. So we'll call foo1 with s as the argument. And then let's print out what happens with ID. So after foo1, ID is, and we'll use the getter for this. And then I'm just going to copy and paste this and do the same thing now with foo2. So let's save this And let's compile and run things. And we see that the ID didn't change after foo1, and it did change after foo2. So we passed the class in by value here, and this line didn't do anything. We passed the sample class in by reference here, and then things were okay. Okay, so of course we can also pass this in by pointer. So I'll change this to pass by pointer, and I'll put the star here. And this complains right away because we want to have the error instead of the dot. Let's change this to 10. And then let's change this to foo3 to be consistent. And then I'm going to copy and paste this again. And I need to declare a pointer to the sample class. So p, give the address of s. And I'll change this to 3, and I'll pass in p. And then let's have a look. Okay, foo3. Let's have a look at how this works. And we see that passing by pointer, things are once again work out. The changes persist. If you didn't actually want to declare this pointer here, you could just do it quick and dirty by passing in the address of s into foo3. And yeah, that works as well. So the last two topics I would like to discuss in this video are the concepts of const qualifiers and passing arguments in by a constant reference. They are slightly advanced, but they do fit in nicely with the discussions that we've been having here, and they are something that you should at least be somewhat aware of. As you've seen, working with references could be quite dangerous. As soon as we place the ampersand at front of a variable, we are giving the method full control to do whatever it wants with that variable. Changes are going to propagate everywhere. What if we wanted to have a read-only method that was to examine the data from the class, and yet we wanted to have an absolute guarantee that things wouldn't change accidentally? So this is where the concept of passing by constant references come in. So I'll make a copy of foo2 to illustrate what would happen. So we'll say that now we're passing by constant reference, and I'll change this to foo4 to be consistent. And if we're going for a read-only method, it doesn't really make sense to be trying to change the ID. So I'll just change this to a print statement saying that we are in foo4, and ID is, and then we'll use the getter here to get the ID. So this looks like a read-only method that we just want to examine some of the data that's in this class. So to ensure that things wouldn't get changed accidentally in S, we're going to const qualify this reference. So we'll put the const keyword here, that now we're saying we want to guarantee that nothing in foo4 is going to change S. And right away VS Code is complaining about this getter. And we're like, well, why? I mean, it's a getter. It's just supposed to get data. But that's because as far as the compiler is going to be concerned, it doesn't know what this getID method does unless we tell it that it's for sure not going to change anything. And the way we do that is we have to const qualify the method itself. So we'll go up to the class definition, and we'll have to throw in a const here in the method declaration. And what we're saying is that we're giving an absolute guarantee that this method is safe, that it just returns ID, that it's not going to change anything in this class. And now we see that down here in foo4, VS Code stopped complaining because it says, well, you want to const qualify this parameter. And I know for sure that anything that happens with this parameter, and the only thing that happens is this method gets called. So everything that happens with this parameter isn't going to change anything about S. So you're safe. So let's save this and compile and run things. Okay, so actually before I do that, I of course have to call foo4 like this here. And I mean, if you're just checking that things work, we're not really expecting anything tricky to happen here. So let's compile this and run things, and we are on foo4. We are getting the latest value of ID, and things are okay. Now, if we try to const qualify the setter, so if I try to put const here, then this complains right away, and it complains because obviously this method is changing things. So if we try to compile this, okay, I didn't save it. Okay, so if we try to now compile things, we see that, well, you know, this is a read-only object, bad things happened, so we can't have the const here. Okay, so that's sort of the idea of const qualifiers and passing things in by constant reference. But now you may say, well, this is sort of silly. Like, why are we having a reference that changes everything, and then we are sticking this const keyword in here to undo that? It sort of sounds like an oxymoron, to be honest. I mean, couldn't we just use this pass by value schematics, and we know that as far as this function foo1 is concerned, it's not going to change anything? Well, the answer is efficiency, because what happens is that when you do a pass by value, whatever is here gets copied into the function in its entirety. So foo1 is going to make an entire copy of this class that's coming in. And okay, this class is small enough, but if you're passing in some big class that has like some image data or whatever, it's really a big waste of memory. And what this does here is that it just passes in the reference. It just passes a link to the class. So it's going to be like 4 bytes. And then we're just sticking the const on here to make sure that things wouldn't go wild on us. Okay. So let's summarize everything that we talked about in this video, and then we will also make a summary of all of the concepts related to pointers and references. So we talked about how references are variables that hold direct fixed links to other variables. We also discussed how references cannot be reassigned once they've been initialized. Then we went on to talk about how references behave with functions. And we once again looked at the 3 different implementations of the add function. In this case, the add function does nothing in terms of propagating the changes back to the calling function, as we're passing the integers in by values. In this case, we are passing the integers in by reference, and the changes do propagate back to the calling function, even when the return type is void. Then in this version, we are passing the pointers in by reference. So this could be used to reassign pointers and have those changes propagate back to the calling function. Then we talked about how references work with classes, and here things were essentially the same. We talked about the 2 versions of foo that do have an effect on s. And then we talked about the concept of const qualifier and passing things in by a constant reference, where if we want to have a read-only function that we want to make sure makes no changes to s, we const qualify the parameter, and then any methods that we execute on s inside this function foo4, we would have to also const qualify, and this is how you const qualify a method. And doing this here, passing in by a constant reference, is more efficient memory-wise than passing in by value. So now let's summarize all uses of star and ampersand in C++. So as we discussed, placing a star at front of a variable in the declaration means you're declaring a pointer, and placing an ampersand in the same location means that you're declaring a reference. Anywhere else, if you're placing a star, that's the dereference operator, which says follow the pointer. And an ampersand means the address of operator, that we're trying to fetch the address of the variable. So references actually came in only in C++. It's not something that's available in C. Like the address of operator is still available in C, of course, and everything to do with pointers is available in C. But references are really a C++ thing. And I would assume someone got really annoyed with the whole pointer notation, so they wanted to introduce something that would make things a little bit simpler. I also wanted to mention that those combinations of the ampersand and star in regular code, they cancel out. So of course, I don't mean like here in the declaration where we're passing a pointer in by reference. I mean, if you see those in the regular code, those would cancel out, because if A is a variable, if we are trying to grab its address and then dereference that, you get A back. And if A is a pointer and you dereference it and then you get the address back, then you get A back. And you can sort of look at the diagrams here. So if A was pointing to X, we dereference to get there, and then we just grab the address of this, so we get back to A. And likewise in here as well. So I can demonstrate this in code. So what I done here is I just declared an integer X and a pointer Y that points to this integer. And then I print X, and then I print star ampersand X, and I print that Y, and I print ampersand star Y. So I can compile and run this. And we see that whether it's X or whether it's star ampersand X, we still get 1. And the same thing for Y, whether it's Y or whether it's star ampersand Y, we do get the exact same addresses. Okay, so that's what I wanted to talk about in this video. Thank you.